Now, a couple words about the number, the magnitude of an electric field. First of all, if there's just a single object, a single pile of charge, a bunch of protons, for instance, and you want to figure out how strong is the field a given distance away, then you can use this particular formula. The Q is the charge of this pile of electrons, and then the distance is the distance between them. In most cases, you're not talking about the effect of a single charge on creating a field, but you've got a pile of protons here, a pile of electrons here, and a pile of electrons here, and protons here, and all of these influence the strength of the field at this location. And some of them are attracting, and some of them are repelling, and at different angles and so forth. The math behind this requires the use of vectors and directions and all that sort of stuff. It's not something that high schoolers in general are usually asked to calculate, but I wanted to show it to you. A computer program could easily be made that could generate all of this stuff, and this is the formula that it's at its heart. But in at least my class, we won't ever use this equation to calculate anything, but it's there. I do want to mention the units. The units of an electric field is newtons per coulomb. And what that means is once you've got this field created, if all of a sudden you show up with a coulomb's worth of charge here, you're going to feel a force. I don't know quite in what direction because we don't have a good map and field line drawn, but you'll feel a force in some direction, and that amount is given by the field strength. So here's a couple of examples, and so we look at some examples. I hope you'll get a feel for these units a little bit more. Deep out in space, far away from stars or planets or moons or things like that, there still is the presence of an electric field. The stars and the planets create enough of a charge here and there that there is an electric field strength, but it's pretty weak. So if you have an entire coulomb's worth of extra charge, which if you saw my other video is pretty impossible to do, you're going to feel only a micronewton, so a millionth of an apple's worth of force, not much. Likewise, or for comparison's sake, in just a typical living room or bedroom, there's probably about 3 newtons per coulomb of an electric field, and that's because you've got lights nearby and you've got electronic equipment, and you may have rubbed your socks on the floor as you walked by and produced a little bit of a charge imbalance, and so all those things added up. In any general time, you probably got somewhere around 3 newtons per coulomb. So if all of a sudden a coulomb's worth of force or a charge showed up in your room, it will be attracted or repelled in some direction with about 3 newtons worth of force. That increases as you get close to equipment like a stereo or a computer or a monitor or something like that, maybe on the order of tenfold. So if that same coulomb's worth of charge all of a sudden showed up near your stereo, it might feel 30 newtons worth of force. In a thunderstorm, the electric fields that can be produced there are a little stronger yet. And then probably the strongest examples of electric fields you might see or experience will be deep inside of an atom. There, you couldn't get a coulomb's worth of charge inside of an atom, but if you could, the amount of force that it would feel would be tremendous on the scale of millions, billions to billions of billions of billions of newtons. Deep inside of an atom, gravity really doesn't matter anymore because the electric fields that are produced inside there are so much stronger. Now, a couple calculations. Suppose I rub a balloon on my head, and I give it some charge, about 350 microcoulombs, which I'll admit is probably more than you can put on a balloon, but what's the field strength 0.2 meters away? So this will be the one and only time that I'll probably use the formula K equals Q over R squared, or the electric field strength is K times Q over R squared. Typically, the field strength is given to you in most of the problems, but here we can calculate it just to get an idea of what this charge might be. So K is that constant 9 times 10 to the 9th. So Q is the amount of charge that I put on the balloon, so 350 microcoulombs, so times 10 to the negative 6. And then the distance is 0.2, and that's squared. So the field strength at this location, just 20 centimeters away from a balloon, would be K times 350 times 10 to the negative 6 divided by 0.2 squared. Oops, forgot the point. 0.2 squared. So, wow, that doesn't seem quite right. Did I forget something? That seems much higher value. Well, maybe that just means, or goes to show that you can't put 350 microcoulombs onto a balloon, but well, no, then again, that doesn't necessarily mean anything. Remember the units for this. This is, how many decimal spots are there? This is 78 million. 78 million newtons per coulomb, and I guess that does make sense. If I could produce a coulomb's worth of charge and put it in this location, then it would feel 78 million newtons worth of attraction towards the balloon, and the balloon towards it. So I guess that is actually pretty relevant now that I think about it. You can't really get that many. You can't get a whole coulomb's worth of charge, so 78 million newtons is actually pretty reasonable. Now, as I mentioned earlier, that equation we don't usually use because when there's more than one charge involved, it just gets too complicated to calculate that. You really need to have computers to do it. What you usually do if you want to figure out what the field strength is in a given location is you pull out a little test charge from your pocket and release it and see what happens, or hook it up to a scale and see what sort of force it feels and in what direction. So if that's the route that you're going to take, if you pull out a coulomb's worth of charge and feel the force on it, or you don't need a whole coulomb, you could pull out a microcoulomb or a nanocoulomb's worth of charge and notice what direction it's being pulled or pushed or repelled. If you use this, figure out the force you feel on it and divide it by how much charge you pulled out, that is the strength of the electric field. So this is kind of a useful formula, but since E is usually given to you, more often than not we're interested in what the force something would feel like. And so if we multiply both sides by Q, you create this formula. That's the force that an object feels is equal to its charge times the strength of the electric field there. So let's do a few examples. What happens if I rub this balloon and I put it near a stereo? How much attraction is it going to feel? So the force that an object feels is equal to the charge of the object times the strength of the field there. So the arrows that are on here simply indicate that those are vector quantities and there's direction associated to them. So the charge is 0.25 microcoulombs, so times 10 to the negative 6 coulombs. And then the electric field strength near a stereo, if we go back and look that value up, that was this, 30 newtons per coulomb. And notice the coulombs and the per coulombs cancel themselves out, so my answer is going to be a force unit of newtons. And 0.25 times 10 raised to the negative 6 times 30 is not a whole lot. Did I do that calculation right? I kind of remember that being a bigger number. But anyway, 7.5 times 10 to the negative 6th. And that would be in newtons. So that wouldn't feel, that wouldn't be too big of a force, but yeah, I guess that is what I've got going on here unit-wise. All right, so anyway, 7.5 times 10 to the negative 6 newtons. So when I did this in class, I rubbed the balloon and I put it near a monitor, and I could feel some attraction, and so maybe that means the electric field strength is bigger near. And I guess what does near mean? Is near like a meter away, or is near like a centimeter away? I put it a centimeter away, so that would definitely have some effect on it too. But anyway, I'm rambling. Let's continue. Suppose I've got a plasma ball in my room. Suppose I turn that on. I'm guessing that creates a little bit of an electric field around it. What if I wanted to try to use that electric field to hover a balloon on top of it, say? How strong of an electric field would be required to make that happen? And then theoretically, if we could balance a balloon, if we increase the strength big enough and put a charge on our own bodies, maybe we could levitate ourselves. So let's draw a quick picture. So here's my plasma ball with all the particles and I don't even know what they're called in front of them. And so here's a little balloon levitating on top of that. The forces that are acting on this balloon, there are two. There is the weight of the balloon pulling it down, and then there is the repulsion created by this electric field that's holding it up. And if this is hovering perfectly, we'll say these are balanced. So the weight of the balloon is equal to the electric force that it feels. And weight, you remember the formula for weight is the mass of the balloon times the strength of the gravitational field there. And then the electric field force is the charge on the balloon times the strength of the electric field there. And if you're thinking there's a little bit of a connection or correlation between these two things, there most certainly is. Mass and charge have a lot of similar properties, and electric field strength and gravitational field strength have a lot of similarities, and we'll dive into more as we go all throughout class. But let's put in some numbers here. The mass of the balloon we said was 10 grams, which is 10 grams is the same thing as 0.010 kilograms. The strength of the gravitational field on Earth near its surface is 9.8. It's the only number we've ever thought about so far, because we don't usually do calculations on other planets, but you could. The units for that could be written as newtons per kilogram, and then this is in kilograms, so newtons is the force unit. And then over here, the charge on the balloon, maybe we can get 35 microcoulombs on there. And the field strength above the plasma ball is what we're looking for. So we'll call that E. When we divide both sides by 35 times 10 to the 6th, I remember this calculation from class the other day, worked out to be 2,800 newtons per coulomb. So a little bit bigger than the stereo we've created, but not outside of the realm of possibility. I think this is something we could potentially create. So anyway, there's a few example calculations of fields and the forces that objects in fields feel. Tune back tomorrow for a video on voltage